Okay, in this example, we're going to talk about the Milliken Oil Drop experiment. We're going to do a brief discussion about that, and then we're going to do an example where we're looking at the mass of a suspended particle, and then we're actually going to take one more step here and do an example where that charge moves. So using a set of parallel plates, Milliken determined very accurately the charge on an oil drop. The way that he did that is he took the two parallel plates and he connected them to a battery with a large voltage. And by knowing the separation distance between the two plates and looking through just imagine a telescope or something, not a telescope, a microscope, at oil drops, he was able to spray a bunch of oil drops in between the two plates. Now what happened is that some of the oil drops would be light, and as a result their electric force would be bigger than, so he'd create a situation where the electric force was going up and the gravitational force was going down. So some of the particles would be too light, and what would happen is that the electric force on them would be greater than the force of gravity on them. They'd fly up to the top of the plate. And some of the particles would be too heavy, and so the electric force on them would be small in comparison to the force of gravity, and they'd fly down the bottom plate. But some of those suspended oil drops would be just right, so the force of electric on them pulling them up and the force of gravity pulling them down would be equal to each other. And in that situation, then the particles could become suspended between the plates. What that meant then, since he could record the voltage very carefully and the separation distance between the plates very carefully and the mass of the oil drop very carefully, is he could get a very sensitive measurement for very small charges. So he could find Q for small charges accurately. And what he discovered when doing this, and I'm going to just simplify the numbers to make it a little simpler, is that he got numbers like 1.6 and 3.2 and 4.8, but he never got numbers like 2.0 or 2.4 or all these other numbers. So by looking at this, what he discovered is that the Q must be some multiple times the charge 1.6. Now what he actually got was times the charge 1.6 times 10 to the negative 19 coulombs. And he labeled that the electric charge, or he considered that to be the elementary charge, the smallest charge that seems to be exhibited on any sort of matter. And that's sort of how he came up with the charge on an electron. Now, we can use that to do some simple problems here. We can figure out what the mass of the suspended particle was. And then we can also use that to solve a problem where the particle moves. So let's work on this one here. Let's say if the charge on the oil drop is 8.0 times 10 to the negative 19 coulombs, the voltage across the plates is 120 volts, and the spacing between the plates is 1.2 centimeters, what is the mass of the suspended particle? Here, I'm just going to erase this stuff here. Eraser, please. Give myself a little bit more space to work. So, we have a charge, Q, is equal to 8.0 times 10 to the negative 19 coulombs. We have a voltage across the plates of 120 volts. And we have a separation, D, of 0.012 meters. So the electric field in between two parallel plates is equal to the voltage divided by the distance between the two plates. So 120 volts divided by 0.012 meters would mean a 10,000 Newton per Coulomb electric field. And with that and the charge, we can come up with the electric force that's acting on this particle. And we get 8 times 10 to the negative 15 newtons. And then finally, since we know if this particle was suspended that the force of electric must be equal to the force of gravity, then that must be equal to the mass of the particle times 9.8 newtons per kilogram. So we get that this particle must have had a mass of 8.16 times 10 to the negative 16 kilograms. You could, of course, solve this problem in different directions, as Milliken would have done in the first place to find Q. So he would have used, by looking at the size of this particle, he would have come up with its mass instead of coming up with its charge directly. And then he would have worked from that mass to determine its charge instead of working from the charge to determine the mass. But beyond that, it's the same basic process. So he would have found this force of gravity first, and then, as a result, the electric force, and then gone backwards to get Q. It doesn't, one way or the other. Let's look at what happens then. If the particle is suspended halfway between the plates and the voltage is turned up to 700 volts, what will be the impact velocity of the charge with the top plate? So here we have the two plates. They used to have 120 and 0, and what that meant was this particle could be suspended. Sorry, that's 120 volts. That particle could be suspended easily, but what if we turn up the voltage? We turn up the power to 700 volts. Well, now the electric force is going to go bigger, and the force of gravity will stay the same. So what that means is this particle is going to accelerate upwards and hit the top plate. Because the force, the electric force acting on this particle is constant anywhere between the two plates, we can actually use Newton's laws to solve this problem. If the electric field is equal to the voltage over the distance between the plates, assuming that we're still dealing with the distance of 1.2 centimeters, then when the field is turned up, or the voltage is turned up, the new electric field will be (58,333 newtons per coulomb). Now, that will lead to an electric force acting on this particle. Keeping in mind that our charge is 8 times 10 to the negative 19 coulombs. Of 4.7 times 10 to the negative 14 newtons. Our force of gravity hasn't gone anywhere. And be careful, an oil drop seems really small, and you might make the mistake of thinking that an oil drop was so small that we can ignore its force of gravity. But remember, it's really only elementary particles like electrons, protons, like really basic stuff that we can ignore the mass for. Something like an oil drop has a ton of particles in it still, and so it still has a significant force of gravity, even though it might seem pretty small. So what was its mass? 8.16 times 10 to the negative 16. Times the 9.8 newtons per kilogram. gets me 8 times 10 to the negative 15 newtons, which I guess makes sense because we had that from before. So if I had this oil drop and I did a free body diagram on it, I'd have 4.7 times 10 to the negative 14 newtons working up, and I'd have negative 8 times 10 to the negative 15 newtons working down. I could come up with my net force. It would be upwards at 3.9, I guess I could have done that in my head, times 10 to the negative 14 newtons per coulomb. Just adding those two, remembering the zero. And then we can use Newton's second law to determine the acceleration. That's a 4. 14. What was the mass? 8.16 times 10 to the negative 16 kilograms. A, is that the mass? Yeah. Okay. So the acceleration of the particle I got 47.8 per second squared. I just want to type that in again. It doesn't seem right to me. Nope, that's good. Okay. 47.8 meters per second squared. This particle was initially suspended. We want to know its final velocity. And what we have here is we said it was suspended halfway in between these two plates. So if it's going to go the distance it's going to travel, it's going to be 0.006 meters, half of 1.2 centimeters. So delta D is going to be 0.006 meters. Okay, so our kinematics equation here, 2AD equals V2 squared minus V1 squared. Remember, I can use this approach because we're saying at least close enough that the electric field between the two parallel plates is constant, and as a result, the force acting on the particle and the resulting acceleration are all constant. So solving that equation, I get a final velocity of 0.757 meters per second. You can solve this problem as well by using an energy approach. You could recognize that if you started halfway in between the two plates and went up to the top, you would have started at a voltage of about 350 volts and moved up to 700. So if you had a voltage change, a VQ, an energy, electrical energy, which is VQ, you have a voltage change of about 350 volts. And then that's going to lead to two forms of energy: kinetic energy and gravitational potential energy. You can solve this problem as well. You'll get the same velocity. I encourage you to work through that on your own, but keep in mind that because it's an oil drop, not an electron or proton, we do have to remember, if we're going to use an energy approach to solve this problem, to include the gravitational potential energy. So that is a very brief overview of Milliken's experiment and a couple little problems.